Hello, everybody. I'm Everton de Oliveira, the Professor Agua from the Groundwater Project. And I'm very glad to bring you the book, The ELMVALE Groundwater Observatory, a facility developed to sample pristine artesian groundwaters for trace elements. And don't be misguided by the title. This book is so interesting. If you work with groundwater, you'll love to learn the things that is in this book. So I have the pleasure to bring one of the authors, the main author of the book, Bill SHOTYK. Welcome, Bill. Very welcome. I really enjoyed the book. And I have to tell that the book has many other authors, co-authors, Mike Powell. We have Beatriz Bicalho, Chad Cuss, Mohamed Javid, Anne Grant Weaver, Michael Krashler, Tommy Nornberg, and Jiansheng Zheng. So many people. The book is very good. It deserved the work of so many people to put it together. Welcome, Bill. Thank you for collaborating with the Groundwater Project, and congratulations for your publication. Please tell us a little bit about your careers and how you ended up together to put this book in place. 9 of you.
Sure. So first of all, thank you so much for all the work that you're doing. And so it was a great pleasure for me to be able to make a small contribution, and a contribution of an idea that I've been pursuing for over 30 years. And the co-authors are some of the people that contributed in very important ways along that journey. So I started out, I grew up in the west end of Toronto, in a very small place. At the time, it was a village, the village of Swansea. It later became part of Toronto. And when I was in the 8th grade, I asked my father if he would buy us a farm. And my father grew up on a farm in Ukraine.
Okay.
And somehow he survived the famine of 1932, 1933.
Okay.
But before that famine, his younger childhood, when he would describe to me life on the farm, very, very simple, very simple. It just sounded wonderful. And so when I was in the 8th grade, as I said, I asked him, would you buy us a farm? And he said, okay. And I said, Toto, it has to be a farm with a river so I can go fishing. Okay, we'll find a farm with a river. And so he looked in the newspaper, and there was an advertisement about a farm for sale with a river. And we went to look at the farm. And the farmer selling the property took us to an artesian spring, which I've never seen before. And there was an old metal cup. And the farmer opened the valve and filled up the cup and drank the water that was coming out of the ground. And I thought, how does that work? So I was literally 13 years old, and the water has fascinated me ever since. So I studied, when I finished high school, I went to the University of Guelph to study soil science and chemistry.
Sure.
Okay, and then I did my PhD at Western Ontario in geology, geochemistry, and a postdoc at University of California, Riverside. And then I moved to the University of Bern in Switzerland, where I created my first laboratory for water analysis. And I thought I should analyze that water from the farm just out of curiosity. Well, it turns out the water from the farm was very clean. So that means I was not able to measure nitrate. I was not able to measure phosphate. And there was only a tiny amount of chloride, less than 1 ppm of chloride. And that water became my in-house reference material for my laboratory to monitor the quality of my instruments. And then when I moved to the University of Heidelberg, so I was 12 years in Switzerland, I moved to the University of Heidelberg in Germany. I became the director of the Institute of Environmental Geochemistry. We set up a ultra clean lab because I wanted to measure trace elements in ice from the Arctic. Okay, and we worked on ice cores from the Arctic with James Zhang, who's a co-author on this paper. And of course, ancient Arctic ice that's thousands of years old is very, very clean. But all the time I wondered, well, okay, what does clean actually mean? And how clean is that water from the farm compared to the ice cores? And I thought, well, this will be a very easy job to measure trace metals in water from the farm, because surely the concentrations must be much higher than ancient Arctic ice.
Yeah.
And when we started to get our results, I was shocked because there was less lead in the water from the farm than ancient Arctic ice. And I thought, well, now this is absolutely fascinating, because ancient Arctic ice we think of as being the cleanest water on the planet because it's distilled from the oceans thousands of years ago before mining and metallurgy.
Yeah.
So this water from the farm, how can it be cleaner than that regarding lead? And so that's when I realized, well, I think I'm going to have to get a little bit more serious about testing of the water. And that's when we started to put procedures in place for proper sampling of the water and analysis of the water to avoid contamination, right? So one way or another, I've been testing that water at the farm, first in Switzerland, then in Heidelberg, Germany, and now at the University of Alberta. 12 years ago, I've been here 12 years now, we built a metal-free, ultra-clean laboratory. And Everton, don't tell anybody this, but the reason for me building that laboratory is to study the water at my farm, right? So the water is so clean, we need special ultra-clean facilities to be able to measure what is in that water.
That's quite, yeah, I never heard such a story. It's so impressive. Very nice. And the book turned out to be very nice as well. And I can see when you talk about it, you show such enthusiasm about it that it is on the book. Congratulations. So tell us a little bit about try to summarize the whole saga of the ELMVALE Groundwater Observatory, because one thing is working, because you're far from your farm. You're in Heidelberg, you're in Switzerland, and then Alberta. That was very far. So how it all started, and how chance helped your hard work to put together this facility.
So Everton, yes, I've never actually lived at the farm property.
Okay.
But it's always in my heart. So wherever I go, I'm taking
it lives on you. That's the other way around.
I take it with me everywhere I go. I take it with me everywhere I go, right? So about this water and the ELMVALE Groundwater Observatory and this book about the ELMVALE Groundwater Observatory. The book, I'll tell you about that separately, because that's my connection to John Cherry, who made all of that possible. But in terms of my colleagues, so when I was at the University of Bern, I was very much supported by the lab instrument company Dynex that was designing and building ion chromatography equipment, right? So with my early work on things like nitrate and phosphate and chloride, I was supported by them.
Okay.
And those measurements back in the old days when I was a young scientist, I was making those measurements myself in the lab. And then when I went to Heidelberg and we worked on the ice cores, of course, working on ice cores, the first thing that we do with an ice core sample, and these were literally collected by James Zhang, the sample has to be decontaminated. You have to remove the outside layers because they're contaminated during sampling. Okay, so you have to decontaminate, and James did all of that. It takes 1 day to prepare one sample. And James prepared hundreds of samples. So you see how much work is involved, right? And of course, for the work that we do on trace metals in water samples, we have to have specially cleaned plastic bottles, right? So we're cleaning our bottles in soap and water and then high purity nitric acid. But because at the farm we're measuring such low levels of metals, the choice of plastic becomes important. So which kind of bottle do you use? Okay, and we're interested in a long list of trace elements. So when we started using, for example, high density polyethylene bottles and low density polyethylene bottles, it became immediately clear the high density polyethylene has much higher vanadium concentrations. And that's because of leaching from the plastic, because vanadium is used as a catalyst to make high density polyethylene. And at a certain point, we decided, okay, we need to have dedicated groundwater sampling wells. And yes, there's an artesian flow at the farm, but it's an old steel pipe.
Yeah.
Okay. So how can we measure trace elements in an old steel pipe of uncertain composition? So that's when we decided to put in a stainless steel well. And once we understood the stratigraphy of the area, because we didn't know anything about the geology, then we decided, okay, let's put in a metal-free well. And the metal-free well, that's special plastic from Denmark. Okay, it's high-density polyethylene, metal-free. But when we did our analyses, we could actually see there's a slightly higher concentration of vanadium coming from our plastic well than from the stainless steel well. So stainless steel is very, very stable. There's very limited corrosion. Okay, but the high density polyethylene must contain traces of vanadium as well in the well. But Everton, because we have a clean lab and because we have great analytical chemists like Michael Krochler, from our plastic well and from our stainless steel well, I'm talking about the difference between 20 plus or minus 1 and 25 plus or minus 1 ppt. Okay, so we're looking at a tiny difference, but we are interested in measuring what is in the water, not the extent to which we've contaminated the water. So this is absolutely critical. Okay, and so when we evaluated the different kinds of plastic bottles, I realized low density polyethylene, it's fine for vanadium, but the lead values were all over the place. And so the only remaining possible source of contamination was ambient air. And because a lot of my research in the past in Switzerland and Germany was measuring atmospheric deposition of heavy metals over the course of decades and centuries and millennia, I knew that the air that we're breathing is contaminated with heavy metals.
Yeah.
So when you go to collect a groundwater sample, when you open the bottle, you've let in the ambient air. Yeah. And because this water is so clean, that's a potential risk of contamination. So I said, okay, we need to have clean air cabinets. So at the farm property, we created the ELMVALE Groundwater Observatory that has specially designed and constructed groundwater sampling wells. They're flowing artesian wells, but the water is flowing inside a laminar flow clean air cabinet, so that when we go inside the cabinet with our closed bottle, we then open the bottle and sample the water in a clean air environment. So Everton, as far as I know, you're the expert on groundwater. As far as I know, this is the only facility in the world where the groundwater is sampled inside a clean lab environment.
That's the first time I've heard of it. Yes, for sure.
So once we had done that, we realized, oh, this water really is very clean, right? And so the concentrations that we're measuring routinely for many trace elements, for silver, for cadmium, for antimony, for lead, for thallium, they're on the order of 1 nanogram per liter, so 1 part per trillion. And these are very low concentrations, right? They're very low concentrations. And the third well that we put in is entirely surgical stainless steel. Okay, and it's now in a deeper aquifer, and it's got a beautiful metal-free clean air cabinet. It's got its own cabin, and that's the well that we're now using to obtain the water that serves as the reference water in my clean lab at the University of Alberta.
Amazing, amazing. Amazing. That story is so nice. And there's another thing. As you tell the story, not only the details of the story, what I realize here is that you are a great storyteller as well, because that we keep listening so, you know, with so much attention. That's very, very interesting. And actually, when I was reading your book, thinking about storytelling, that's what I had in mind when I read it. I was thinking about the episode of Cosmos 2 with Neil deGrasse Tyson. And, you know, we have all the professional guys, the storytellers that put things together. And one of the episodes tells about the contamination with lead. And that's your one of your expertise. So what are the challenges for lead in groundwater when we compare to surface water analysis?
There's actually a lot of challenges, and Everton, I'm actually very glad you're asking that question, okay, because lead is really our single most important trace element indicator of the impacts of human activity on the environment, okay? So, you know, atmospheric lead contamination in Switzerland, we've documented the origin of that more than 3,000 years ago in Switzerland using a peat bog. And that's the beginning of atmospheric lead contamination dating from the period of the Greeks, okay, from silver mining. Silver is recovered from lead ores. And then we have the contamination from the Romans 2,000 years ago, medieval Germany, the Industrial Revolution, introduction of leaded gasoline, and so on. So we see all of that in the bogs, we see it in the ice cores. So we know, for example, in Southern Ontario, because we've studied bogs in Southern Ontario, we know that an average square meter of soil, forest soil, garden soil, agricultural soil, doesn't matter, the average square meter of soil will have 1 gram of industrial lead, okay? So I did some work in Southern Ontario, again, just out of curiosity, okay? When I was on a summer vacation with my daughters, they were very young, and we were at my parents' summer cottage on a lake, I said, hey, let's go out and sample some water for measuring lead in the lake, in the streams, and so on. And so we could see from the isotopic composition of lead that we have leaded gasoline slowly migrating out of the soil into the lake, okay? But the water samples in the middle of the lake were really very clean. So isotopically, we could see it's industrial, but from the perspective of the concentration, they were quite low. And I assume that's because of particles settling and scavenging and so on. So there's natural purification processes. So we started out by asking the question, how much of that old gasoline lead is leaching into the surface waters, okay? And then the question became, okay, how much is going into the groundwaters? And that's when we started analyzing the water from the farm from that perspective. But to answer that question, we have to be able to measure lead at the very low concentrations found in the groundwater, and those concentrations are extremely low. So Everton, even though I shouldn't tell you this because the book has almost been published, okay? I'm not done with the lead question. I'm not done with the lead question. I'm not yet happy with our measurements. The plan for us now is to collect 1 liter bottles of water from the ELMVALE Groundwater Observatory. In my clean lab in Edmonton, we will evaporate that water, okay, down to 10 milliliters. And now we have a 100 times increase in concentration. And then we're going to remeasure the water. Okay, because we want to be measuring lead at values that are well above our limits of detection. So right now we're approaching the limits of detection of ICP mass spectrometry. So I want to increase the concentrations in the water by evaporative concentration and then reanalyze. So I will keep you posted on those results.
Please, please. I'm wondering here, wouldn't you lose a bit of the lead into the evaporation process, because it's quite tricky to get that done, I believe, right?
Yeah, I don't think so, because the lead is going to be present in non-volatile inorganic forms. Okay,
Yeah.
But Everton, I think part of the story on the lead and many other trace elements, they have a tremendous affinity for various types of particle surfaces. Okay, so what is happening is lead is being adsorbed onto clays, lead is being absorbed onto organic particles and so on. So if the groundwater has very low concentrations of particles, it will also have very low concentrations of lead.
Yeah, true. Makes sense. Makes sense. Thank you. Well, we have a visitor here, I guess. Hello, Mike. Thanks.
I don't know what kind of an apology to offer. I apologize as much as possible for being so late.
No, that's okay. That's okay. We've been through half of it, but we'll have time to listen to your stories. We're having fun here, so I'm pretty sure you're gonna add to that on your site
as I join. So I know that you've been in good hands, because nobody is closer to this work or more dedicated to this work than Bill is. So I know you haven't been bored.
Very good, very good. So, guys, I have the next question is, anyone that works seriously with groundwater samples, particularly for environmental purposes, they have faced the problem of analyzing low concentrations in groundwater, from sampling to bottles to lab procedures to interpretation. You know, the whole thing I've been through for all my life, and I'm still struggling to get it all done. From your experience, what does your book, being very practical, what does your book offer to the readers on how to handle all these difficulties? Because there are so many. And by the way, I liked your the slogan of your lab, Mike. We can measure almost nothing. That was very good. For people who works with low concentrations, that's lovely. Please.
Okay, so Everton, Mike, I'm going to take that question because it's an analytical question.
Okay,
you bet.
So Everton, yeah. So that slogan at the swamp lab, we can measure almost nothing. Yes, that's a play on words, and that refers to the swamp lab at the University of Alberta. So just for your listeners to understand, that's we don't study swamps, even though we would like to, and they're fascinating and beautiful. It's a metal-free, ultra-clean lab for studying trace metals in soil, water, air, and plants, right? And the letter M stands for manure, but we haven't analyzed any manure, but we needed an M in that name. Okay, so Everton, you've remarked about my ability to tell stories. Thank you.
Yes.
That's very kind. So I'll tell you one more. When I started the work on measuring lead in groundwater, when I was still at the University of Heidelberg, I reached out to colleagues in Germany and the USA and other places about measuring lead in groundwater, because it was making me crazy how difficult it was. And each of them said, Bill, why are you having such a tough time? It's really easy to measure lead in groundwater. We measure it all the time. And it took me a little while to figure out they were only measuring their own contamination. right? They weren't actually measuring lead in groundwater. And so Everton, it's not my role to pass judgment on other people's work generally, but in this book, we've tried to explain how difficult it is to measure lead in groundwater. And again, I'm holding up lead as that example of that single most important indicator of the impact of human activities on the environment, right? And
Yep.
just to give you some context, I'm a big fan of titanium alloys, and a lot of our peat bog coring equipment is made in titanium. James Yang helped to develop the titanium corer for coring the ice core in the Canadian Arctic. So I'm a big fan of titanium alloys. And I thought, hey, we're going to build the first groundwater sampling well in titanium, okay, because titanium alloys are so stable, it'll be the cleanest water samples. And I thought, well, to be safe, let's do some leach tests. So Tommy Nuremberg, who's one of the co-authors, mechanical genius, he can build anything. He was in Denmark at the time. Today he works at the Swamp Lab at the University of Alberta. But I gave him some titanium alloys, and he made some water bottles made of titanium alloys, and we leached them in nitric acid. And I was shocked how much lead was leaching from the titanium alloys. So then I reached out to one of the world's leading experts on titanium metallurgy. And I said, hey, what's the deal? You know all these different alloys. Like, where's this lead coming from? And he said, Bill, I'm shocked. Like, I absolutely no idea. So Everton, the first question is, if you want to measure metals in groundwater, what material are you going to use for the well? And as you know, because you're a professional hydrogeology person, okay, there's a lot of groundwater sampling wells in PVC.
Oh, yeah.
Okay.
Yeah.
And what metals does PVC contain? Lead and cadmium. Okay. So I would not have any PVC on our property anywhere near our wells. I haven't looked at the leaching characteristics, but I'm not going to use a material that contains lead, right? And
Yes.
then, so there's the issue of the wells, there's the issue of the bottles, okay? And as I said, in the end, the one that we decided upon is polypropylene. In fact, my entire lab at the University of Alberta is made in polypropylene. I love polypropylene. It's very, very clean. But again, it has to be cleaned in water and soap and nitric acid. We also use hydrochloric acid. So nitric acid is good for dissolving particles, for leaching metals, for oxidation. But hydrochloric acid, that chloride helps to bind lead and further improve the blank values, right? So there's a cleaning procedure. So in this book, we describe the well materials. We describe the bottles that are being used, the cleaning procedure that's being used, and then Everton, the icing on the cake is those clean air cabinets, right? Because then we're eliminating the problem of contamination of ambient air, right? And that's how we arrive at the point for measuring the concentrations of trace elements in the water. But Everton, I do want to point out to you, one of the exercises in the book refers to an experience I had with the Ontario Ministry of the Environment. And I was giving a presentation to them at some point, some years ago, when it was early days on measuring metals in groundwater. And they were very kind and very respectful, and they listened. And I did point out in my presentation, when I measure trace elements in groundwater, and they measure trace elements in groundwater in the same area of Southern Ontario, their values are 1,000 times higher for lead and chromium, 1,000 times higher. And they said, Bill, we understand that. That reflects the methodology we use. But our mandate is not to determine how much lead or chromium is in the groundwater. Our mandate is to find out whether the levels in the water are below the values that can affect human health. So if the values that they have are below the drinking water guidelines, they've done their job. So Everton, I understand that. I understand that. But as a scientist, here is my problem. Here is my problem. As you know, there are people who model groundwater and groundwater evolution. And if they go to a database and they get information about trace element concentrations in groundwater, and they do their calculations of mineral dissolution and mineral solubility, and they decide, oh, well, the lead value is 1,000 times greater than what it should be, it must be colloids. They have to introduce some process to explain that data, when in fact, it may be analytical. So the ELMVALE groundwater facility is a facility designed to determine what is actually in the water and not the extent to which we've contaminated the water. That's the difference.
That's very good. That's very good. I liked it. Another thing is, if you like, you know, the ELMVALE groundwater, it's like Eagle. You use as short for the long name, and it became almost your alter ego, right? Because that's you've been working all your life. So is the groundwater there? You know, you mentioned that it's cleaner from the Arctic region. How is that? And why is that? Because I was reading a book. It's what the hell? Because you know, such a clean water is rare, right? It's very rare. You always find something. Maybe it's a cross contamination because very few people have the facility that you have for that. But then you found that before you had the facility.
So Everton, here is the deal. Yes, I love the name EGO, right? These acronyms I think are important, but you have to have a pretty big ego if you think you can easily measure what's in that water, okay? It's a difficult job, okay? But you've asked the $64 million question. You've asked it, why is this water so clean?
Exactly.
Okay. Now, I have to be perfectly honest with you because and I'm going to hand this over to Mike in a second, but I need to be clear on a concept, okay? So, in addition to the ELMVALE Groundwater Observatory, with the help of Mike and many other people, we created the ELMVALE Foundation, which is a federally registered charity for environmental education. And he and I both have given many public lectures, okay? So how do I explain at a public lecture to a farmer or to a cottager or to a businessman who has little or no scientific training, 1 part per trillion of lead? How do I explain that? Well, the easiest way to do that is to explain that ancient Arctic ice is considered the cleanest water on Earth, and our water is much cleaner than that. Okay, so then people started to call this the cleanest water on Earth. And what I can say is that's a philosophical question. And really, to determine the cleanest water on Earth, I would have to test all of the water on Earth. And I won't be able to do that. But that came from an explanation, right? It came from an explanation because I'm trying to share these results with the people that live in the area, because ultimately, Everton, my other goal is to protect this water for future generations, okay? But John Cherry, I dragged him up to this area at some point a few years ago, and he said something about pristine groundwater. And, you know, I took him to the artesian flow in ELMVALE at the side of the road where the water is just gushing out. And he stood there and he looked and he said, Bill, I don't understand this at all. Where is this water coming from? Where's the water going? Why is it so clean? And he's the world's leading expert on groundwater and he doesn't understand it. And I said, hey, you've used the word pristine groundwater. What do you mean by pristine? He said, Bill, pristine means less than 5 parts per million of chloride. And I said, oh, well, our water has less than 1. And he said, no, Bill, no, that's impossible. There isn't any water with less than 1 ppm of chloride. I said, oh yeah, it's this water. And I showed him my data from the University of Bern that I measured myself 30 years ago. Plus we have data from University of Heidelberg, University of Ottawa, University of Alberta. It's under 1 ppm of chloride. So what did John Cherry say? John Cherry said, Bill, I've never seen cleaner groundwater anywhere. And he studied groundwater around the world. So I think it's pretty clean water. But Everton, why is it so clean? Okay, I have some ideas. I think they're quite crazy. Mike is a real geologist. He's now done a lot of field work in the area. Mike has been my geology teacher since we met as graduate students. Okay, so I defer the question to Mike. Mike can tell you why this water is so clean.
Oh, okay, Mike. Is he your friend, Mike?
Yeah, I like the pressure. What can I say? But here's the truth, Everton. If I could tell you why, we wouldn't need this project. We'd be all done.
Sure, yes, true.
So, look, it is, Bill mentioned that you're a hydrologist. You know how complicated hydrogeology is. Yeah. So it's not like we don't know the important geochemical, microbiological, hydrogeological processes that are going on. We know about all of those, but what we don't know is how they have all combined to produce this pristine water. And you know, Bill is a soils guy, and he's very much focused on the soil environment, which we know is absolutely one of the most important filters for groundwater. Yep. Ian Clark at University of Ottawa will be focused on looking at the isotopic data so that we can figure out the age and sources, etc. Beth Parker at University of Guelph believes that some of the water is bubbling up through the ancient rocks at the bottom of the 125-meter deep valley through which this groundwater travels. Okay. The OGS knows that one recharge area is 16 kilometers to the east of our site. Then we have the precipitation, and then we have what might be considered fossil water that is stuck in the last glacial sediments to be laid down when Lake Algonquin disappeared between 13,500 and 16,500 years ago. And this whole system of lithofacies going from the surface down 125 meters is extremely leaky. So there's vertical exchange of waters between and through aquitards, between aquifers. It has potentially 4 different sources. We know now that microbiology is critical in analyzing any groundwater, very, very important in the evolution, the electron donor acceptor concept and controlling redox. We certainly know that the mineral chemistry and residence times of the water as it sits in the soil pores is extremely important. We know that carbonate equilibria is one of the factors in this area, except we're not finding as much carbonate as I would have expected. So we have all of these things, biotic and abiotic. And what we have to do is we have to find out through experimentation what role each of these contributes, and then try to figure out the relative importance of each of these in producing the final product. So we've said that we'll need 5 years to do this, and I think that will do. And we will have all of these experts, Guelph, Ottawa, Alberta, and the Ontario Geological Survey, and they know more about this water than, I mean, as far as the watershed goes and the lithostratigraphy, they are the experts. They've punched a lot of holes in the ground up there. And we're going to put all of this together and try to come up with a story that will not only tell us how this water formed, but how we might look for similar types of hydrogeologic settings to find more of this water. And or I'm sure you're aware that many large companies in Canada are involved in water purification around the world for whole
Yes.
cities, et cetera. And they like to use local materials because they can't, these local communities can't afford big, expensive projects.
Yeah.
Why not look for those materials that we know will be important and use them in the same ratios and relative to each other? I mean, it would be, they're building water purification plants now out of local materials. Why not use a model that we know does a great job? So listen, I think the things that we will reveal in the 5-year project will be amazing. I think they will be ground changing. Bill just recently sent me a new article from Nature Communications on what's called dark oxygen, this water that is contained in oxygen is contained in places where we wouldn't expect it, and the role of microbiology in producing it. So we just have a lot of interesting to learn. We've got some of the world's best people to figure this story out. So if you want to ask me this question again in 5 years, I'd be very happy to give you the answer.
Very. I was thinking here, because this is such a different thing, because usually we model, you know, the geochemistry for water with concentrations, but without. That's very tricky. I'd love to see how you handle this situation, because, you know, with such low concentrations, anything could be wrong, right, on our interpretation of the models, correct?
Yeah.
So
So Everton, if I can just add, just to be clear, sorry, Mike, for your listeners. So Mike is referring to a grant application that we're working on with Ian and John and so on to study these waters, right? This is a suggestion from John Cherry a few years ago, which, you know, I'm paraphrasing here. Okay, Bill, you've been doing this as a hobby. Now it's time to get serious and bring together the team and do a proper study to understand this water, right? So Everton, I'm so grateful to you for helping to bring our scientific efforts to this point, because literally this book is the springboard then for us to launch this proposed new groundwater study. So yeah, like Mike said, in 5 years' time, if you would call us up again, then Mike can explain why this water is so clean.
I'll keep that on my you know, my agenda. No, I'll ask you 5 years from now and see what we have. It'll be interesting to see how it develops. Very good. So guys, this book for me, it's, you know, like when I was thinking, it's not like a Pandora box, because Pandora box brings lots of bad things. That was the opposite, brought lots of great surprise for me that I couldn't grasp from the title, because the title shows the thing there. So I'd like to thank you very much for this wonderful work and wonderful big book. So what is the audience that it's meant to reach? I have one in mind, because I made up my mind after reading the book. So what would be the public? But you may have something else in mind. What do you expect? And how did you put together the book in the first place? And what is basically the main audience that you expect?
I wish somebody had asked at the beginning what the audience would be. That would be helpful, because it's written now. But Everton, I think anybody who has an interest in trace elements in the environment, anybody who has an interest in trace elements in groundwater, and anybody who has an interest in the relevant parts of analytical chemistry, and I would say people that are interested in the natural filtration of water. I was about to say water by soil, because Mike knows I think everything is happening in the soil zone. But I agree with a lot of what Mike has been saying during the past years about the importance of all of these water-bearing, unconsolidated sediments. right? Soil scientists, we have a hard time thinking below that, a horizon, right?
Yeah.
But what I wanted to say is what we see here is the interface of all of these things, trying to understand how does Mother Nature create this perfect water, right? This perfect water. And then we can ask the question, are there things that we can do as a society to protect areas like this, and also to use these materials in other areas to purify water in sustainable, low energy, efficient ways?
Good. You, Mike.
I love to smile when Bill talks about soils because he's so passionate about soils. And I apologize, I didn't know you hadn't broached the subject of the project we're planning yet. And I don't know if Bill has already told you that through another grant that he received at University of Alberta, we have a few nests of lysimeters now sitting in the highlands and the terraces and on the clay plain, and those nests were sampled all summer. Waters have been shipped back to the University of Alberta, and they're being analyzed through a variety of techniques. So this will be the real first trace element geochemistry of these waters. It's not to say that other analyses haven't been done, but as you know from talking to Bill, they haven't shown the real concentration of XYZ element in these waters. So, I mean, I think to a large degree, what we're going to end up with, and it's one of my things to talk about, is, well, I should finish that thought. When water leaves the bottom of the soil zone and it travels, whether it goes straight down 125 meters or whether it travels 16 kilometers along one of these lithophases, the water will change who knows how many times. We know at every aquifer, aquitard interface with change in microbiology and redox. We know that with every change in mineral type that it comes across, you get a change. It's going to get dirtier in some places. It's going to get cleaner in others. But we have to know the total picture of what happens to it just before it comes up out of the ground, and we get to sample it. That's the key. And there's going to be some extreme challenges there. Bill has very, very strict guidelines for anything that touches the water in any way, as you've heard. And then we have hydrogeologists that want to put holes down and pump the water out like they do, or introduce tools to measure various parameters. And then we got the isotope people and the microbiologic people, and they don't really care about either one. So it really has to be a very, very well integrated and very, very clearly thought out project. My hope is that through all of this work, we can convince the governments, whether local or regional or provincial or national, that the system of permitting the taking of water or surface mining, land use change, which now has a single tier of evaluation criteria, has to be changed to a multi-tiered approach, because it's hard to stand in the middle of Ontario and tell people there's a problem with water. My God, every direction you take, you need a boat to get out of here. You know, the bottom line is everybody sees water everywhere, but all water is not created equal. And that's a fact. And what we have here is the most pristine water that we know of anywhere on the surface of the earth. It's a natural analog to be studied because it's a scientific curiosity. But this should lead government to say, hey, we can't permit changes in land use and or water taking in this one little watershed when it has so many good answers to give us in the future. And we can't treat all water the same. We have to have a tiered system for permitting land use change and resource consumption and protection. And that to me would be an amazing outcome. So yes, it's going to be a real challenge to put all this together, but I think the people that are involved are up to it. And I think that the answers are going to be amazing. And I think that we will find out that whether it's the soils or the lithostratigraphic units or the distance the water travels within them, or the leaking back and forth, or the contribution from the old rock at the bottom of the valley that's filled now with glacial sediments, all of that stuff's going to go together. It's all going to have an impact. And by the way, I've been doing here in London the first scanning electron microscopy and EDX work, and we'll be doing the first XRD. And what we're finding mineralogically in the 3 sites that have the lysimeters in them now is very surprising to me. And I'm not going to say much about it other than that these soils have a mineralogy that I was not prepared for. Mainly feldspars and heavy metals or minerals with heavy metals in them, not very, very little carbonate for the most part. Clays, but we haven't been able to isolate the clays yet. We just know the general spectra. So every little bit of information that we learn is going to help us with this, and it's going to show people why the typical criteria that you see written up in hydrogeo reports to governments for land use change or resource use just isn't appropriate.
Yeah. Well, thank you for your answer. I really enjoy that, and I can tell you that there's so many facets that we can get from the book itself, from practical aspects on how to sample, how to use, how to analyze, and a deeper understanding, because we have to interpret the clean water, which is such a novelty for hydrogeologists. We're always dealing with bad water, right? That's most of our situation. So it's very nice, guys. Unfortunately, I'm loving our chat here, but our time is up here. Please make your final considerations.
Bill, go ahead.
Oh, Everton, I was just going to say that this area that the farm is located in, it's a very important part of Canada in regard to Indigenous peoples and the history of the province in terms of being the interface between Indigenous people and the people that came to North America much later from Europe. And I've learned a lot from Indigenous friends about their perspectives on water and the importance of water. And they look at water in a very, very different way. And that's been really eye-opening. And again, Everton, as a scientist, I want to understand the water. And we've documented our ability to do that. And then the other thing, which is not written in the chapter, but it's certainly in our public lectures, about the importance, I guess we did mention it in the book, the importance of protecting such precious water for future generations, right? So I want that message to come out.
Thank you very much, Mike.
Okay, I think it's very, very important to realize that the only way this project works is because of the lab that Bill has established at the University of Alberta. I often tell people it's the only lab of its type in the world. I'm pretty sure I'm correct on that. There may be some like it, but I don't know where. Bill would be better to answer that. But it's because we have this laboratory, this tool to use, that we will be able to answer some of the most important questions. And I think that is an extremely important issue. And finally, and of course, covered very well in the book chapter. The other thing is that sociologically, NSERC requires now in their funding a lot of partnership, connections, and ways of disseminating information. Because Bill brought up the Indigenous attitude of water, I will be on Christian Island next week. Bill doesn't know this, so don't tell him. Okay. I will be on Christian Island next week with the Anishinaabe Council. They have officially partnered with us, and we will be working for hours on developing indicators of change and how the science, the data, the findings of this project can be integrated into their teaching and outreach, and how they, as a group of people, can teach us more about how we should approach the scientific aspect of water. And through that, we will both become better at what we do. So and we have partners in education and environmental, we have 12 different partners now, and we're working on a few more. So we're really going to be able to spread the word. It's going to be an amazing collection of people.
Thank you, guys. I'm just enjoying too much the conversation here. We were supposed to end in 40 minutes and now more than an hour, but it's a very lovely conversation for such a nice book, such a nice work. Congratulations for your work. Like I told you, Bill, I hope I can visit your alter ego there, right? See if I can connect to the site, see that, because the book's so good. Right, and I hope I'll meet you there. If you're not in Alberta, you'll be there sometime. Why not? It's gonna be fun.
I will be there from May till October, and you and Bruna are invited. And there's a place there for you to stay. Just give me a little bit of advance warning, and you can see the water and hear the water and taste the water. And I'm sure you'll enjoy it.
I'm pretty sure. Thank you guys very much. Congratulations again for such a nice work, and we'll meet you. We'll meet again in 5 years from now. Okay, take care.
Thank you so
Thanks,
much.
Everton. And I
I
apologize for my tardy.
No, you're welcome. Don't worry. We understand that. Thank you very much, guys. Bye.
Thank you. Take care. Bye-bye.
You too. Bye, guys.
Bye, everybody.